First, we join Patrick Moore for The Sky at Night.
Good evening. For once, some really good news. Funds have been provided for Manchester University's new large radio telescope, which will actually be set up at Cambridge. It's part of the Merlin network, which is centred upon the Lovell telescope at Jodrell Bank, that most famous of all radio dishes. Radio waves are forms of what we call electromagnetic vibrations. Visible light makes up only a small part of the total electromagnetic spectrum. To one side we have the short waves, ultraviolet, X-rays and gamma rays, and to the other side we have infrared and radio waves. And radio waves are collected by these instruments known, rather misleadingly I feel, as radio telescopes, which are really more in the nature of large aerials. But recently we know we've had a great surge in the development of a new generation of optical telescopes, and the same thing is happening with radio telescopes. A whole new generation is coming along, and of these the very latest is the Australia telescope. And that's why I'm doubly glad to be joined now by Dr Alan Wright from the Parkes Radio Astronomy Observatory in New South Wales. Welcome to The Sky at Night, Alan.
Thank you.
It's fair to say, isn't it, that by now optical astronomy and radio astronomy are fully integrated.
Yes, indeed. I mean, if we imagine the whole spectrum of electromagnetic radiation as a sort of gigantic piano keyboard, then the tune of optical astronomy, that is using light, is played on just the central 2 or 3 notes of this keyboard. Radio astronomy is played on a couple of dozen notes in the bass, and the other astronomers, infrared, ultraviolet, X-ray, etc., they make up the rest of the keyboard. But in order to hear the symphony that the universe is playing to us, then we have to have the whole keyboard.
Well, I mentioned the Merlin network just now, and that's composed of several individual telescopes. Jodrell Bank, of course, the smaller dishes at Darnhall, Warthall, Knockin and so on, and soon to be joined by the new one at Cambridge. Now, these are individual telescopes, but working together, they can in fact make up a radio telescope which is as powerful as it would be if it covered a large slice of England.
The history of radio astronomy has shown us that in order to really understand the universe, we have to be able to observe both faintly and finely. Now, by faintly, what I mean is that we have to be able to detect vanishingly small quantities of energy, possibly from the edge of the universe. But by finely, I mean we have to be able to see very fine detail in the centers of these objects. For example, in the quasars, when we look at the quasars with our ordinary coarse radio telescopes, then we merely see a rough, blurry picture. But when we have one of these synthesis telescopes, many telescopes linked together, we're able to get a very fine, detailed picture of what's going on. And we think what we see, though we're not quite sure, is that there is a massive black hole at the centers of these quasars, swallowing whole stars. But to be sure, we need to be able to map them in very fine detail.
Do you remember George Ellery Hale, the great optical astronomer, who masterminded various huge telescopes, including the Palomar 200 engine? His call was always for more light. He wanted bigger and bigger telescopes. In the same way, you radio astronomers want larger and larger telescopes. Ideally, Alan, how big a radio telescope would you like?
Ideally, we'd like one as big as the world, but that, of course, isn't possible. It would even settle for one as big as Great Britain or Australia. But radio astronomers realize they can get the same effect as a great British dish, for example, by taking away carefully selected parts of the dish. Of course, this partial telescope can't receive as much energy as a large dish, but as regards seeing fine detail, it does the job very well indeed.
We do have one great advantage. We live on a spinning globe, and you radio astronomers can do some very clever things by making use of the Earth's rotation.
It depends upon where the radio source we're observing is and how the Earth is rotating precisely. But the basic idea is very simple. Imagine we just have 2 telescopes. During the course of 24 hours, the Earth rotates, and these telescopes spin around and synthesize a band just as on the Great British Dish. Now, of course, if we can bring the energy from the individual dishes together in the right sort of way, then we can get the same effect as though we had a Great British Dish. Let's try and make this easy. Imagine that we had England, for example, at the North Pole. Now, during the course of 24 hours, the Earth rotates once. And each of the telescopes sweeps out a band, just as we had before. Now, provided we can somehow bring the energy collected by the separate telescopes together, a few well-placed telescopes are almost as good as our great British dish, provided we wait long enough.
But how exactly do you make these various separate telescopes work together to show you this fine detail?
Well, again, imagine we had just two telescopes. Depending upon the position of a radio source in the sky, light, or radio waves in this case, will arrive at one of the telescopes slightly before the other telescope. The difference in time of arrival at the two telescopes, however, depends upon the precise position of an object in the sky. By accurately monitoring the arrival times of the radio waves at the two telescopes, we can get a lot of information about the position of a radio source in the sky and also about the fine detail in it.
In theory, it's very simple. In practice, of course, it's anything but that. It must be a very difficult task to make these various separate radio telescopes work together.
Yes, there are two methods of doing it. Let's say we consider just two telescopes in the Merlin array. The energy arriving at the telescopes can be brought together by radio links. The other way of doing it is to actually use video recorders, rather like the ordinary domestic recorder that you might be recording your television programs with. The idea then is that energy arrives at the two telescopes and is recorded. Then, well, perhaps long after the observations have taken place, the tapes are brought back together again and played back in exact synchronization. And by doing this, it's possible to combine the energy. The problem, however, is that in order to synchronize them, we have to have extremely accurate clocks so accurate that in the course of a million years, they perhaps have only lost or gained a second or even less.
And that's a great improvement on the timekeeping rate of the Earth itself. And of course, the Australia telescope is of type 2.
Yes, mainly. However, the Australia telescope will use both sorts of bringing the energy together. In the case of the 6 dishes, radio telescopes, mini telescopes at Kulgura in the northern part of New South Wales, the energy will be brought back together directly by links of the first sort. On the other hand, as we move south to Mopra, which is near Siding Spring Mountain, the site of the Anglo-Australian telescope, then we will begin to use video recorders. That will also be true of the Parkes radio telescope, where I work.
And I've been there, of course. I've been inside the dish.
And further south still, it gives us the potential to bring in telescopes like that at Hobart in Tasmania, and the great dish near Tidbinbilla, which is near Canberra, which belongs to NASA.
Fair to say, isn't it, that the longer the baseline you have, the more accurate the telescope?
That's true.
Well, what about going into space, then?
Well, one possibility is actually being explored in 2 projects, one which is American, one which is Russian. These are called the Quasat, and the Russian one is called the Radioastron project. The idea here will be that we don't even have to have these telescopes. If we're recording them, the data, we don't even have to have these telescopes here on Earth. And the idea is to put one out on a satellite. That will give us phenomenal capability to see fine detail.
Well, we're certainly having this new generation of radio telescopes now, so let's turn next to what they're telling us. You know, in the early days of radio astronomy, it was rather naturally thought, I think, that bright stars such as Sirius, Rigel, Vega and so on, they'd be the main sources of radio emission from the sky. And of course, bright stars are not generally powerful radio sources. Why not?
Well, radio telescopes best detect things which are either big or hot. Now, by big, I mean things that cover an appreciable fraction of the sky. And by hot, I mean temperatures considerably greater than just the few thousand degrees that ordinary stars have. Unfortunately, most of the stars in the sky are not big enough, they're just point-like, and they're not hot enough to be easily detectable in radio telescopes. In fact, the Sun, for example, if it were put at the distance of even one of the nearest stars, would be totally insignificant in our radio telescopes.
All the same, radio astronomers used to talk about radio stars. I remember that too.
Yes, but they were wrong. They were completely wrong. What happened was that the early radio surveys showed up mainly big extended sources like the Crab Nebula. But there was also a few radio sources that were far smaller than the Crab Nebula. Now, because they were essentially point-like in the radio telescopes, they were christened the radio stars. Actually, what happened is that they, of course, turned out to be the quasars, gigantic exploding galaxies, millions and millions of times further away than real stars.
All the same, in a way, we've turned the full circle now, haven't we? Because although I realize that the bright stars don't normally send out detectable radio waves, there are now some certain kinds of stars that are quite strong radio sources.
Yes, in the last 10 years or so, radio astronomers have been able to detect stars that somehow make themselves bigger or hotter than on average.
Well, there are various kinds of radio stars. I mean, consider P Cygni. Now, P Cygni can be seen now in the evening sky. It's in the famous constellation of Cygnus that I think most people will recognize. There it is, the cross shape with the bright first magnitude star Deneb, nearly 70,000 sun power. And look near the central star of the cross, Gamma Cygni. And close to that is a little arc of stars, and there is P Cygni, shown on the diagram just below the foot of the letter P. It's just visible with the naked eye, magnitude just about 5, although it is decidedly variable. It's very luminous, it's very remote, it's also extremely unstable. And in fact, Alan, it seems to be doing its very best to blow itself to pieces.
Yes, well, of course, all stars are producing huge quantities of radiation at their centres, and this radiation has to fight its way out to the surface. Now, large stars produce more radiation than smaller stars. In fact, they not only produce more radiation, they produce enormously more radiation. A star perhaps twice as massive as the Sun, for example, produces not twice, but 8 times as much radiation. Now, this means that the very largest stars, the mass-loss stars, stars like P Cygni, are producing so much radiation that they're actually blasting off their outer layers into space. Now, with radio telescopes, we've been able to map this gas blasted off into space and been able to say in great detail what's happening at the surface of stars and how the matter is being thrown off.
And what's going to happen to P Cygni eventually?
Well, although it's throwing off huge quantities of gas, in fact trillions of tons a second, it won't change its total mass very much. And that means it will go through the ordinary sort of evolution processes that we think applies to high mass stars. Now, a very funny thing happens. The higher mass stars actually live less long than the small mass stars. They're burning up their energy at such a prolific rate. And therefore, we think it will eventually run out of fuel and end up as a dead star, essentially a white dwarf star.
That's some way ahead yet, even so. And what about the so-called super hot stars?
Well, there are many different sorts of extra hot stars. One of them, the most famous prototype, is probably, one we've been studying just recently at Parkes in particular, is in the constellation of Canis Venatici.
Hunting dogs, just near the Great Bear.
Right. And the most famous example is RS, which of course is a variable star designation. RS Canis Venaticorum, isn't that a marvellous name?
Lovely name, yes.
Anyway, RS CVN stars, we think what's going on here is as follows. There is a fairly ordinary, rather sun-like star, and close by there is a red giant star. These are really quite close together. Because they are so close together, the binary motion of the two stars stirs up the insides of the red star and produces enormous star spots on its surface.
What exactly are these star spots?
We think they're enormous violent interactions of magnetic fields and atomic particles. And from time to time, as these mix up, they let loose with enormous radio flares. In fact, we've been able to compare our radio observations made at Parkes with some made by Arthur Page and his group of amateur astronomers in Queensland.
Yes, I was out there recently, in Mount Tambourine. It's got a wonderful setup there. Yes.
And Arthur and his collaborators have produced some very important observations that shows that the light level from these RS-CVN stars is going up and down. This happens as the binary star rotates, and from time to time we are presented with a star spot towards us. We get less light than usual. We were able to show that our radio observations flared, we had actually flaring going on at the same time as the star spot was pointing at us. And this really put the cap on the model and showed that we were probably on the right track.
Well, it shows the power of radio astronomy, because after all, when you look at a thing like our scan then, it merely appears as a point of light. Now, we can now show it as a globe with spots on it. Are you absolutely confident that that's right, and that there are star spots there?
Well, we'd like to be confident. The star spots we're suggesting are enormous things, whereas sunspots are such that you might say that from time to time the sun has just a mild case of measles. In the case of the RSCVN stars, they actually appear to have third-degree burns.
Must be an amazing sight seen from close too. Well, let's turn next to those fascinating things which really do intrigue me enormously, the so-called symbiotic stars, real weirdies.
Well, another Australian radio astronomer, David Allen, and I have been working very intensively on the model of one symbiotic star in particular. Of course, the symbiotic stars are stars that can't seem to make up their mind whether they're very, very hot stars or very cold stars. When we take optical spectra of them, we find that there's strong evidence that they're both hot and cold at the same time, completely paradoxically. David Allen and I have been able to put together all the information we could get our hands on, and what we find is, we think we find, that there is a big red giant star which is blowing off its outer layers, but very slowly, much slower than the P Cygni stars. It's a dusty, dirty sort of star. Lurking close by, there is a tiny white dwarf star, a star that's essentially run out of all fuel. The wind from the red giant star piles up on the white dwarf star, giving it extra fuel to burn and a new lease of life. This causes the white dwarf star to have strong energy, strong radiation, and also to blast off a wind on its own. And now there's an enormous battle begins to rage between the dirty red giant and the flashing white dwarf, because this event is called a helium flash. And the winds collide in a mighty bang in between the stars. And we think we've put together a good picture of what goes on. But the final details will probably have to wait one of the great radio telescopes, probably the Australia telescope, when we're able to map it.
Do give us a preview. What's going to happen in this Star Wars?
Well, from time to time, the white dwarf wins the battle, and it blasts out more wind. And this means that the red giant sort of cowers down on itself. The battle is carried to the red giant. But then, from time to time, the white dwarf gets weaker and tireder. Less wind comes out of it. And so the red giant expands to fill the space around. What's going to happen in the end, we're not absolutely sure, but we think it's something like that the white dwarf will eventually die away, the red giant will go through its normal evolution, and it will become a white dwarf too. And so the battlefield will be essentially deserted apart from two tiny, minuscule stars.
Are there many of these symbiotic stars?
We know of a few hundred, but how many more there are around, we don't know. In fact, we think that there are probably many more cowering in this dirty red wind.
Well, it shows, as I say, this shows the power of radio astronomy. And what do you think is going to be the next great development?
In radio astronomy, I think we've still got to see the benefits of the large synthesis telescopes, such as we've been talking about. I'm sure the Australia telescope is going to make enormous impact in the southern hemisphere, where probably, I would argue, most of the interesting objects are. Whether or not that's true, I don't know. The other thing that's fascinating in radio astronomy is, of course, the idea of putting telescopes out in space, but that's a few years off yet.
You know, radio astronomy is a young science. I can remember the time when it didn't exist, and it's amazing how much it's told us in a comparatively few years. And I'm sure we're going to learn a great deal more in the very near future from the Australia telescope and others like it. And next time you're in England, Alan, I hope you'll come back and tell us what's going on there. Meanwhile, thank you very much.
Love to.
And next month, we're going to come very much nearer home and talk about Earth-grazing minor planets, one of which, 65 million years ago, may have wiped out the dinosaurs. Who knows? Good night.